will be showing you Lab 1 constant velocity today. Here's our introduction. So we rolled a marker across the table for this lab and we calculated its constant velocity. And our purpose was to observe and predict the motion of the marker moving with constant velocity using a computational model. And so we used Tracker, which is a video analysis tool, to calculate the velocity of the marker to be this value. And we used GlowScript to model it. So here are our principles and models. We use kinematics, simple motion, so no forces, coding and computation in GlowScript. We use momentum principle, which is Newton's second law, as well as the models being a scatter plot model, a position versus time, velocity versus time graph in GlowScript, and a GlowScript computational model. Here are the equations we used in this lab. So we have V average equals delta V over delta T, which is our average velocity equation. We have our position update formula, which is position final, equals position initial plus V average delta T. And our velocity update formula, which is V final equals V initial plus F net over M delta T. Here are our initial conditions. So we have our coordinate plane here, which is what we set up in Tracker to be our 0, 0 point. We have our blue meter stick here, which is what we use to calibrate our initial units and the distance. So we matched up the blue line and gave it the same distance as the distance on the meter stick. And so the marker's net force, since it's constant velocity, is 0 here because we edited out the part where you're actually pushing the marker. So this part where you actually see the push is edited out of the software used in Tracker. And we set the marker's mass to 1 kilogram, which we'll talk about later. Here's the experiment. So we use Tracker here. It's a very similar photo to before. And each time we pushed on the marker, we would move the time step forward by 0.33 seconds each frame. And so it would, each time we pushed on the marker, it would progress it forward and it would put this data into the table. And here's our code. We have our initial position, our initial velocity here, and we have our calculation loop, which follows Newton's second law and updates every time step of 0.33 seconds. And here is our computational model, right here. And as you can see, it moves to the right in the positive x direction. Here is the tables and data. So we have our observed versus predicted position in the x direction. So the green is our GlowScript data and the red is our Tracker data. And so they're very similar, as you can see, except that the GlowScript data has a higher initial and final velocity. And this is probably due to the initial velocity being slightly higher in the Tracker video it's slightly higher as we computed because it's being pushed. So because it's being pushed, even though we edited it out, there's still that initial velocity being higher since there's a force applied. And so for our what if, so if we flipped the axes, our velocity ends up being in the negative x direction and our magnitude of the velocity is the same because velocity is a vector, so it has magnitude and direction. So only the direction changes. And so what does it mean? So if we had net force equal to 0, that means that we had an upward force and a downward force applying on the marker, which are the upward force from the table and the downward force from gravity. And so to conclude, in this lab, we calculated the velocity of the marker using Tracker, created a computational model in GlowScript to represent its 2D motion and of the marker moving with constant velocity. And so we used Newton's second law to calculate the instantaneous velocity at each time step. And however, the velocity of the marker is constant, so the velocity at each time step is the same. And we visualized it through a scatter plot, which was made in Excel, and a visual model on GlowScript. And so here are assumptions and sources there. So for our assumptions, we assume that F net is equal to 0 since we're starting the video when the marker is moving at a constant velocity. We assume that the initial velocity is equal to the final velocity since there's assumed to be no net force since it's constant velocity. And that's just from editing out the pushing of the marker. And we treated the marker as a point mass, and we gave it 1 kilogram as its weight. because the force does not matter for constant velocity. So in the lab, it's 1 kilogram. And for our source of error, we have that the distance is slightly off because we're pushing the marker, but we're also editing out our marker's push. And so our initial velocity is not the exact same as our final velocity. And we have our human error in clicking the points in tracker, which, as you saw in the code earlier, it resulted in a small velocity value in the y direction. And that's it. Thank you.